Well, hello everyone. I'm Jim. I'm the CTO at Irreducible, and I'm going to be talking today about a proof system that we're building called Binius, which is a hardware-optimized SNARK proof system. But to tell you a little bit about what Irreducible is building generally and what we're about, we're a cryptographic acceleration company. That means our focus is to build highly performant and cost-effective proof clusters for zero-knowledge and verifiable computing. We use a combination of hardware optimization, cryptographic innovation, and hardware-software co-design to achieve this. And Binius is the result of our research efforts in both cryptography and hardware and high-performance software to build a better proof system to bring the cost of proving down by what we think will be ultimately another 1000x, which can unlock a whole lot of new use cases. And this is extremely important. I talk about cost because I do think that cost and performance is the main thing that is holding back good user experience and the application space that could be using verifiable computing but isn't. So let's start by talking very high level about what proof systems are out there today. You have two major categories of SNARKs. There's elliptic curve-based protocols and what I call STARKish protocols, which are a little more nebulous, but based on coding theory, hash functions. The fast Reed-Solomon IOP of proximity is central to STARKs. And elliptic curve-based protocols give you small proofs, which are very fast to verify, but slower to prove. And they support some nice cryptographic properties like folding schemes. You must use a large finite field, and large finite fields are more expensive than smaller ones. And in our hardware prototypes, we learned that this is a compute-bound computation when you're communicating with an accelerator over a PCIe bus. Whereas STARKish protocols, you end up with larger proofs, but they're a lot faster to prove. And I put that twice. And you can also use smaller prime fields to use STARKs, but you can only go down to about 32 bits for technical reasons I'll talk about a bit later. And in our prototypes, we learned that when we're communicating with an FPGA accelerator, we were bandwidth bound and not compute bound. The other thing that has been discussed in the previous two talks is we now live in a world where proof recursion is extremely efficient and practical and essentially necessary to build really scalable proof systems. This is a diagram from Polygon about showing how their ZK EVM works, where on the top layer, you're actually proving EVM transactions, and you have several layers of recursive proving to incrementally compress proofs that started out as being fast to prove but large, and ending up at the bottom layer with a proof that's extremely small but relatively more expensive to prove. Two other things about modern SNARKs. It's very common to use hash functions that are not your traditional SHA-2 hash function or Blake2 or whatever, but to rather use Poseidon, which is optimized for SNARKs and verifiable computing. Poseidon has become semi-standard. And we have a new technique called lookup arguments, which have made it so that you can express more like bitwise operations in circuits without having to emulate the entire circuit in zero knowledge. So I'm going to start with a motivating example, which is the Keccak 256 hash function. This is basically the hash function enshrined in Ethereum, and it's the #1 bottleneck for ZK protocols scaling Ethereum today. Here are four proof systems that all are proving Keccak hashes, and they're roughly proving about half a megabyte of data being hashed. And I benchmarked on GCP, and we can see that Halo 2, while having very low verification time, is extremely slow. It's 261 seconds on an 11-core machine, whereas Plonky 3, which is pretty much the state of the art for STARKish protocols, is 16 and 20 seconds. Actually, this has come down to 5 and 8 seconds, respectively. And Binius is now faster than both of them. It's at also about 5 seconds as compared to 5.3 for Plonky 2, Plonky 3. However, if you want a recursively friendly proof, you would use the Plonky 3 with Poseidon 2. And so basically the trade-off is we have faster prover time with our new proof system, large proof size. The rest of this talk will be about how we achieve that and what Binius actually is. So to create a fast proof system, we need to understand the major components of what a prover does. The first thing a prover does is a step called witness generation. This is not particularly expensive, but it's a little tricky to parallelize. You then need to commit the witness, which you may have heard of these operations, number theoretic transforms, Merkle tree building, or in the case of elliptic curve SNARKs, multiscalar multiplications. The vanishing argument is essentially either a sum check protocol or the univariant quotient. It basically is lots and lots of polynomial evaluations. And then the last step is the opening proof, which is kind of the fanciest and probably hardest to understand, but is actually not that expensive. So here's where the various provers spend their time. We can see that these labels are flipped. This is actually Plonky 3 with Poseidon 2. Almost 75% of its time is spent doing the commitment phase, which is the number theoretic transforms in the Merkle tree building. With Plonky 3 with Keccak, when you have a faster hash function, it still accounts for almost half the time, whereas with Binius, we've basically eliminated commitments as a computational bottleneck and now have a different bottleneck, which is the vanishing argument. So why is committing so slow for Keccak or for Plonky 3? Essentially, to understand the arithmetization, which is the circuit of how you verify a Keccak hash function in Plonky 3, we know that it uses this error arithmetization. Each permutation, which is the fundamental operation in Keccak that we want to verify, is 24 rows of the trace. And each row commits about 2,300 1-bit columns, meaning you need to commit field elements that are 32-bit field elements, but only take the values 0 or 1, and you also need to commit a few hundred 32-bit elements, which are 16 bits. However, in order to commit a single bit element, you have to pad them up to a full field element, which means you have this really slow operation. You're trying to commit a single bit of data, but you have to pay 32 times the cost in order to do that because of the field size. And so when we understood this is what led us to ask the question, could we build a proof system over bits natively? This is a phenomenon we call embedding overhead. So the question is, can we commit small values faster than large values? And for any sort of traditional hash function like Keccak, you're doing lots of bitwise operations, which is why these single bit field elements arise so frequently. With elliptic curve commitment schemes, the answer is sort of yes. It gets tricky when you get down to about 1 bit, or when you get down below 8 bits, but committing smaller values down to 8 bits is faster than large values. With Fry commitments, you can't really get any faster going below 32 bits for technical reasons that we'll see later. But with Binius, we can basically commit bits without paying any additional overhead. And I like to think about this as saying that the commitment scheme maximizes the information density of the committed data. So what is Binius? Binius, as I said, is a new proof system based on research we did at Irreducible and some papers authored by myself and my colleague Ben. And Binius combines arithmetization over a different type of finite field than any other proof system uses. These are binary fields. It's a multilinear polynomial protocol based on hyperplonk. This has become a popular technique that's also used in Jolt and Spartan and so on. The commitment scheme that we use is a generalization of breakdown, and we also have a version that generalizes Fry, which is used in SNARKs. But they both eliminate the embedding overhead during the commitment phase so that you can commit bits as fast as you can commit larger field elements. There are a couple of other cryptographic contributions. So we need the key unlock here is using binary fields for the proof system. So what does that mean? Well, finite fields roughly come in two flavors commonly. You can have prime fields or you can have binary fields. Prime fields are basically the integers modulo some prime number. So adding field elements is basically the same as adding integers. Multiplying field elements is almost the same as multiplying integers. However, with binary fields, they're a little less familiar. Binary fields can be expressed as polynomials over bits modulo some irreducible polynomial. Don't worry if you don't know what those words mean. Addition is just the XOR operation. So the idea is you can take a string of bits, you can add them together, and it's just XOR. And multiplication is complicated, but is actually far more efficient in hardware than integer multiplication, because you do not need to propagate carries. So if you can think about how you multiply integers together in grade school, where you have to keep track of the carries and keep moving them, that does not happen when you are multiplying binary field elements, and that saves a lot of hardware cost. So this is kind of how binary fields behave, and specifically a type of binary field called a tower of binary fields that we use. So we can take a string of 128 bits, and we can interpret it as an element of this 128-bit field, f2 to the 128. But we can take that same string of bits and interpret it instead as a vector of 4 adjacent 32-bit field elements. Or we can interpret it instead as 16 8-bit field elements or 128 1-bit field elements. And this is just a memory cast. It's the same string of bits that we can view in several different ways based on the size of field element that we want to operate on. This is we call this packing throughout the cryptography papers that we write about, that you can take small field elements and pack them together into large field elements and pay no cost in doing so. Here's some math that describes what's going on, but it's actually quite easy to explain. The smallest field is f2. It's the bits 0 and 1, multiplying them as AND, adding them together as XOR. If you can recall from high school when you learned about the complex numbers, you took your real number line and then you added one more element that was not on the number line, and you got a larger, you went from the number line to a plane. That's basically what we do here. We start with f2, we add a new element, which is a root of this polynomial, and that brings us into sort of a two-dimensional space, and we will continue doing that. And we'll find basically a new element that doesn't live in that space and add it. And now we have a four-dimensional space, and so on up until, basically forever. It was proved by this mathematician in 1987 that there's a very nice and deterministic way to construct these fields. And then it was observed that there's extremely efficient multiplication and even field inversion algorithms for this construction. The gist of this slide is that we have a clever way of using this packing property of binary towers to avoid padding our elements. So instead of taking single-bit elements and padding them up to 32-bit field elements, we can instead take 32 single-bit elements and pack them together into a 32-bit field element, and then do error-correcting codes on top of that. And this is fundamentally different from prime fields that have to be over 32-bit primes. So this is how we arithmetize the Keccak circuit in Binius. Each Keccak permutation can be viewed in two ways. If you recall from what I said about Plonky 3, each permutation was 24 rows. In our case, it is still 24 rows over 64-bit field elements, but that is the same when you unpack it as 1,536 rows of bits. And each row has only 60 committed columns as opposed to 2,300 and 80 virtual columns, which we do not need to commit, but we can still operate on nonetheless. Those are shown in kind of these cyclic rotation columns. And we have far fewer constraints because we have far fewer columns. A lot of the power here comes from the fact that we define these virtual columns, which are bitwise rotations of the committed columns, and this bitwise rotation operation comes up in the computation of the Keccak hash function. Now, I really haven't said much about what makes Binius hardware friendly. All I've told you is that we can reduce embedding overhead and we can get somewhat better performance on CPUs. But the story really gets interesting when you look at hardware. So again, we approach this from the hardware perspective where we have a computer and we have an external accelerator connected over a PCIe bus. When we are bandwidth bound, we want to maximize the information flow between the host and the accelerator. And when you have to pad your elements up to 32 bits, you're just killing your bandwidth utilization. So the fact that we can maximize the information density of our committed data lets us transfer, way more information to the accelerator. Not only that, the underlying arithmetic is much more efficient. As I said, binary fields simply, because they have carryless multiplication, require less logic utilization. So I'm going to give you some numbers on our FPGA estimates from our hardware team. We've prototyped all of these in FPGAs. The way to think about this is area is the number of logic gates in a circuit, and then you have to run that at a clock frequency. And area times delay is an efficiency metric that effectively is the inverse of how many operations you can perform per second. So in this case, lower is better. It's less area times gate delay. So Mersenne 31, which is basically the fastest 31-bit prime field you could possibly construct, has this efficiency of 84,000, and a 32-bit field is about 5 times less expensive than that. In our case, we're actually able to use the 16-bit field very often, which is another 4 or 5x over that. And amazingly, the 128-bit field is only a little over 2 times less efficient than the 31-bit prime field, which is extremely notable because the 128-bit field is required for cryptographic security. When we compose these into some of the other computational bottlenecks like number theoretic transforms, we see that our NTT efficiency is also outperforming very efficient 31 and 64-bit primes by another 4 or 5x. And really, this gets interesting when we look at recursion-friendly hashers. So the Poseidon hashers are basically the most verification-friendly hash functions that you can use for prime field settings, whereas in our case, we have proposed a new hash function based on existing work called Vision Mark 32, which is natively defined over towers of binary fields. And this needs only 4 million gates as opposed to, which is like 10 times less than Poseidon 2, which is the most recursion-friendly 32-bit prime field hash function. But we can also arithmetize Grostel, which is a hash function that was in the SHA-3 competition and is fairly standard and extremely efficient on CPUs as well. And amazingly, Vision is only, I think, 30% less, more gates required to verify a natively ZK-friendly hash function than a traditional hash function in, in native digital logic. So, this is basically what led us to try to figure out how to make binary fields work. And our plan as Irreducible is to build a kick-ass open source software implementation of Binius for everyone to use. And we are also building proving as a service using our custom FPGA accelerated technology to, basically give a 100x reduction in cost and improving time. We think we can achieve something like that. And here's some links as to how to follow our progress. That's what I got.